All right, the last talk in this session will be given by Marco Scigliuzzo. And the title of the talk is Higher Coupling in a Philip Chip Architecture Transmon-HBAR System.
Okay, thank you for the introduction. Thank you to sticking to the last talk of the session. First, I want to apologize. Evgenii couldn't come here because he didn't get his visa, so I'm going to give his talk on his behalf. My name is Marco Scigliuzzo. I'm from Tobias Kippenberg Group in EPFL in Switzerland. And today I want to talk about our recent result on coupling HBAR to a qubit. So just a bit of motivation why we are interested in mechanical system. Well, mechanical system have a mass. This means that they are sensitive to all the force, acceleration, other mass. And indeed, you know that gravitational waves have been detected with massive objects. And now it's even possible to couple mechanical system to superconducting qubit, therefore encoding non-classical state, and then you can start to think to have or to study interesting effect of gravity on these quantum states. Furthermore, phonons do not propagate in vacuum, so their lifetime can be very long. This means that if you go in the classical technology, you can make timing machine or time-keeping machine. But then in the quantum regime, in the quantum technology, you can have quantum memory that have extremely low crosstalk and very long lifetime. And finally, the speed of sound is much smaller than the speed of light. This means that you can have extremely short wavelength. Therefore, again, in technology, you can make a very compact filter. But if you go in the quantum application, you can have giant atoms, meaning atoms that are span many wavelengths than the radiation that they interact with. And there has been many platforms that has been coupled from superconducting circuits to mechanical system. You have surface acoustic waves, thin film suspended membrane, superconductor mechanics, defect in photonic crystal. But what we're going to concentrate today is this bulk acoustic resonator. So these are effectively mechanical modes confined between the two edges of a substrate. And the excitation is simply given by applying a oscillating voltage on a piezoelectric material. And since this system is effectively as big as the thickness of the substrate, you have intrinsically a multi-mode system. And therefore, the idea is very simple. Now you have an intrinsic multi-mode resonator. What happens if you make an array of this system? Well, you can start to think about having many phononic band structure. And now this is even more interesting because you can couple a superconducting circuit to it, therefore having an effective photonic solid-state simulator. So this is our main motivation, so let's try to build the system step by step. So the first idea is to couple the qubit to the HBAR. This has been done in different architecture as I show. And what we basically do is building our circuitry on a simple silicon wafer with standard superconducting qubit fabrication. And in order to couple the HBAR to the system, we just put a flip chip on top. And this little piece of piezoelectric material, this aluminum nitride, for us effectively give the coupling between the HBAR and the qubit excitation. And if you simulate this architecture, you indeed see that all the electric field is going to be confined between your top. The laser is not very visible, but it's confined between the top and the bottom part of the two chips. And in principle, you can calculate or extrapolate from this simulation the effective coupling and see that you can have qubit HBAR coupling as high as 12 megahertz. But for the rest of the talk, we are just trying to address or target gaps that are more closer to 1 micrometer. So this is our fabricated device. As I mentioned, the bottom chip is standard fabrication on qubit on silicon, and the top flip chip is effectively a very thin 100 micrometer thick silicon wafer with a stack of molybdenum and small aluminum nitride shaped resonator. And when you flip chip the system, when you flip chip the top chip on the bottom one, you indeed get this assembly that is shown here. So the first measurement is simple. We just want to do qubit spectroscopy. So as I mentioned, the effective HBAR is a multimode mechanical resonator. Therefore, if we sweep the frequency of the qubit, we are expected to see many level cross. And this is exactly what we measure. And importantly, as I'm going to show further, this coupling is quite large, is around 4 megahertz. And of course, if you keep going, tuning the frequency of the qubit, at some point you will reach the readout resonator, and you will just get audit cross with it. So the first step is also characterizing the qubit lifetime. And here we already see some effect of this piezoelectric coupling. We have effectively 2 qubits. We have an HBAR qubit that again is coupled to the mechanical system, and a simple reference qubit. And if you measure the lifetime of the reference qubit, our fabrication, maybe here it wasn't perfect, but you can measure something like 4 microseconds. But then if you measure the HBAR qubit far from the 2 resonance, so here where the orange line is placed, you will see that the lifetime decreases more than half. And we believe that this is mainly due to the piezoelectric unwanted losses to the HBAR. Of course, we can tune the qubit and try to do some time domain measurement, as it is done here. So the protocol for this measurement is quite simple. You excite the qubit, you move it. In this case, it was through Stark shift, but again, we can also move it via fast flux pulsing, and then read out a different time delay. And you can see that as the qubit move along its frequency landscape, you enter many mechanical resonance, and effectively you're just swapping mechanical excitation with the qubit excitation. If you go further, what you can do, you can indeed prepare a mechanical Fock state. This again has been done by a few groups, but we are just retaking those steps. And the protocol here is again quite simple. You can excite the qubit when you're not in resonance with the HBAR. You tune the qubit in resonance, you just wait a Rabi time, so effectively you swap the excitation of the qubit with the HBAR, and then you move the empty qubit back. And in this case, you effectively have a mechanical Fock state that is indeed already a remarkable state to have. And then, in principle, you can, again, wait sometimes and then retrieve the excitation, just redoing the procedure in the opposite way. And effectively, here, what you can measure is the population of the retrieved qubit, and as a function of the waiting time in between the two protocol, and effectively measuring the lifetime of the single Fock state. Again, compared to literature, this is maybe 2 orders of magnitude lower, but this is our first attempt. So just to conclude, I show you that indeed we have the HBAR qubit coupling, and the coupling is quite large, is indeed 4 megahertz. But I mentioned that we want to couple to HBAR and eventually many in order to have a phononic band structure. And indeed, if you now choose an electric model of your HBAR system, you can imagine that just sharing a common capacitance between the two HBAR, you will have an effective coupling. And you can simulate this in console, and effectively here you see that now the single HBAR just have, okay, with the laser you cannot really see, but the second HBAR is just connected or close enough to have common capacitance. And effectively from COMSOL simulation, you can also calculate how much coupling do you expect. And effectively here, you can measure, or you can have an effective coupling of over 140 megahertz. And importantly, if you compare now with the line width that we already achieved, you can already think that we are pretty close to get a strong coupling between the two HBAR. So again, for future measurement or for future iteration of the device, another main step is to increase the mechanical lifetime. So with this, I arrived to the end of my talk. I want to thank all the circuit team and Guzovskii member group, and especially Evgenii that couldn't be here today. Thank you for your attention.
Do we have any questions from the audience?
For your qubit, when you change the T1 change, is the coincidence?
So for the T2, probably the filtering wasn't really good. So we believe that okay, when it's limited by piezoelectric, maybe we don't have enough coherence. We are still T1 limited, so we don't have enough time to see the effect of the bad filtering. But then as soon as you move a bit, we see that. So I mean, if you want, it's a coincidence in the meaning that we are right there to see the bad filtering effects.
What's the coherence time? Did you say
So, I mean, other group like Ian Chu, the coherent time of single Fock state in HBAR system have shown even hundreds of microseconds. Our system is a bit different because we strike for larger coupling, so we have an effective intermetallic layer that is superconducting in between the piezoelectric and the substrate. So we believe this is an additional scattering point for the phonons. But from simulation, maybe you should have 50 microseconds at least, but we are not sure. So it's we expect more than this, and we are indeed trying to improve that.
Yeah, if I can have a last question.
Okay, there was one. It's okay.
Sorry if you in the flow suite, there's these disconnects between the discrete regions. What causes that?
Sorry, which one? This one?
One was, here and on the slide.
Okay.
In particular, in the top color plot, you see there's the usual curve, but then there's these breaks.
You mean this second below?
Yeah.
You mean this?
No, I mean, in the uppermost curve, as you go to
About strong coupling.
Say it again.
I think he's talking about these strong coupling crossings.
You mean about it cross?
Yeah, so
Okay. These are basically strong coupling between HBAR. So the HBAR is indeed the multi-mode, and effectively you have just avoided cross between each of different modes.
So my question was actually about the satellite curve that you see underneath.
So it's probably two photon excitation of the qubit.
Okay.
So you see the harmonic of this qubit, it was maybe around 150, and this is maybe 50 megahertz or 70 megahertz. So maybe just too strong coupling, too much strong driving for this measurement.
Thank you very much. Let's thank our speaker and also all the speakers of the session one more time and conclude the session. Thank you.